In this video, we are going to discuss how to derive the geodesic equation. Okay, let me write the heading down. How to derive the geodesic equation. So how to derive the geodesic equation. Just writing the heading down. Okay, so that's the topic for this video. So let's get to it. So first, when you're doing this, obviously you're gonna do it on a specific manifold. So suppose that your manifold is a three-dimensional manifold, because you can, if you want to, you can look at a two-dimensional manifold. You can work on a two-dimensional manifold. And also, three-dimensional, four-dimensional, or, high-dimensional manifolds. But we'll just work from the context of a three-dimensional manifold. Okay. So we're going to derive the geodesic equation. That's the purpose of this video. So let's begin. So let's say in a 3D manifold. Okay, so I'll say in a three-dimensional manifolds. In a 3D manifold, with coordinates. So suppose the coordinates are U1, U2, and U3. So we'll say with coordinates. With coordinates U1, U2, and U3. So these are the coordinates of our three-dimensional manifold. So U1, U2, and U3 are the coordinates of our three-dimensional manifold that we are working in. Okay. Now, also suppose that the position vector, all right, the position vector or the parametrization of the manifold that we're working in is given by the following. Okay. So the parametrization of the manifold we are working in is given by the following position vector. So we have U1 dependent. So you can see here that the parameter that we are working with is S. And in this case, S stands for the arc length. Okay, so we've got RS, that's the position vector of the manifold. Okay, so this is the first component is U1 of S. Okay, the vector multiplied obviously by the vector E1. So the E1 basically, this just shows the E1 is a base vector. Okay, so that's a base vector. So we're expressing this position vector in terms of this basis. Okay, and the basis of vectors are E1, E2, and E3. So let me just write the rest of the components. So you got U1 of S, E1, U2 of S, E2, okay, plus U3 of S, E3. So that's how we express. So we express the position vector in this way. This position vector obviously is the parametrization of this three-dimensional manifold that we're working in. Now, you can express this position vector also using index notation. So you can express it in the following way. Okay, you can express it as UI by EI. You can also express it like this. This is using index notation. All right, so you can also do this. Now, let's look at the tangent. Okay, let's look at the tangent to this manifold, the tangent to the manifold in general. So let me say the tangent to the manifold that we are working in. So we'll say the tangent to this manifold, the tangent to this manifold is given by, so we say the tangent to this manifold is given by the following. So we will express or represent the tangent with a lambda. All right, so we'll do it like this. This is the tangent to this manifold. It's given by lambda is equal to the following. So to get the tangent, you differentiate the position vector. You differentiate it with respect to s. So that's r dot. So the dot basically denotes the derivative of this rs with respect to the arc length s. All right. So lambda, which is the tangent to this manifold, is given by the derivative of r of s with respect to s, denoted with an r dot of s. So this is the same thing as the derivative of this r of s, which is the position vector of the manifold, with respect to s. Okay, so this is basically the tangent to this manifold with respect, or expressed in terms of the arc length s. Okay, so that's how you express a tangent vector in this manifold. Okay. So let's move on. Okay. This tangent over here, we can also express it in the following way. So you can write this tangent like this. So obviously, this tangent, this is how you can express it. First of all, as a derivative of the position vector. You can also express it in general in terms of the basis that we are using, okay? In terms of the basis of this manifold, which is a E1, E2, and E3, okay? So you can express it in terms of the basis, and obviously in index notation, or before we express it, before we write it in index notation, let's write it like this. So it'll be lambda 1, that's the first component of this tangent. You can express it like this: lambda 1 multiplied by E1, which of course, that is the first component, or the component of the tangent along the base vector E1. And we've got lambda 2 by E2. We've got lambda 3 by E3. All right, so you can express the tangent to this manifold in this way, okay? And in index notation, you can also express it like this, obviously. You can also express it in index notation in this way. So now that we have this, we can move on and state the following. So now, there's a condition of geodesics. Okay, there's a condition that that geodesics satisfy. All right, and this condition is called the straightness condition, and it applies, for example, to geodesics in R2. So let me just write this down, and let me say one of the conditions for geodesics is called the straightness condition. Okay, one of the conditions for geodesics, is called the straightness condition. The straightness condition. So this is one of the conditions for geodesics. It's called the straightness condition. The straightness condition. It basically, well, it applies, for example, okay, it applies for example, okay, it applies, for example, to geodesics in R2. Okay, it applies, for example, to geodesics. It applies, for example, to geodesics in R2. Okay, so it basically states that all right, it basically states that the tangent vector lambda basically states that the tangent vector lambda does not change direction along a geodesic. So it basically states that the tangent vector lambda doesn't change direction. Let me rewrite that direction. The tangent vector lambda doesn't change direction along a geodesic. Along a geodesic. Okay. All right. So, i.e., I'm gonna write the next thing on the next page. Okay. So let me read that paragraph again. So it's one of the conditions for geodesics is called the straightness condition. It applies, for example, to geodesics in R2. So it basically states that the tangent vector lambda doesn't change direction along a geodesic. Okay, so this is called the straightness condition, and it's one of the conditions that geodesics satisfy. It especially applies, obviously, to R2. So now, what does it imply, though? Okay, what does this straightness condition imply? Well, it implies the following. Therefore, the rate of change of the tangent vector, okay, with respect to the arc length is equal to 0. Now, this is of course for a geodesic. So for a geodesic, we have the following. For a geodesic, we have the following condition. We have the following condition, and the condition is the rate of change of lambda, which is the tangent along this geodesic, with respect to the arc length, is equal to 0, because this is because of the straightness condition, that the direction of the tangent vector along the geodesic stays the same. All right, the direction of the tangent vector along the geodesic stays the same. So that's where this condition that's where this condition comes from. All right, so that's where this expression comes from. Now, what does it imply? Well, it implies the following. So the rate of change of lambda with respect to arc length is 0. So that implies the following. So we just want to substitute what lambda is. All right. Now lambda, obviously, we know that lambda is the tangent vector along the geodesic in this case, and we also express lambda like this. as we showed earlier, we also express lambda in this way. We got lambda I, EI. So we also express lambda like this. So we substitute this expression of lambda, and that is equal to 0, obviously. And then we go ahead and we differentiate this. We're going to apply the Leibniz rule, also called the product rule, and to differentiate this. So when you apply the Leibniz rule or the product rule of derivatives, you get the following. You got the d lambda I with respect to x multiplied by ei plus lambda I multiplied by the derivative of ei with respect to lambda. I mean, sorry, with respect to the arc length s. That is equal to, of course, 0. And so this, we can write this, of course, using dot, the dot notation. So this is the same as lambda dot I, okay, multiplied by ei, our base vector. And this, of course, is equal to, we have lambda I, and this derivative, we can also write it as e with a dot I. Okay, let's go back there, e dot I. And this is equal to, of course, the 0 vector here. So now we have this expression. It's an equation. We have an equation, and this equation, of course, is an equation that a geodesic will satisfy. So this is an equation that a geodesic will satisfy because it comes from the straightness condition that geodesics satisfy, particularly in R2. Okay, so it's going to lead us to a general geodesic equation. All right, it's going to lead us to a general geodesic equation that geodesics in general, in any manifold, that satisfy this. Okay, it's going to lead us to an equation. What I mean is that it's going to lead us to an equation that geodesics satisfy in general, and this is for geodesics in any manifold. All right, so let's continue. Now we have this expression, so we're going to move further. Okay, so moving further, we look at the basis vectors, ei, and c. What we can say about them. Well, the basis vectors. The basis vectors. Okay, basis vectors ei. The basis vectors ei are equal to the following. Well, you can express the basis vectors of this manifold in the following way. You can take the position vector and you can differentiate it. Okay, so you do a partial derivative of the position vector of the manifold, and you do a partial derivative of this position vector with respect to the coordinates. Okay, so ui. So you go ei is equal to the partial derivative of r with respect to ui. So that's a way of deriving the basis vectors, or of calculating the basis vectors for a manifold. So then also r itself, the position vector r, as you saw earlier on, we expressed it in the following way. So we'll say this will give us the following. So we go partial derivative with respect to ui. Okay, and we're going to substitute what rs is in terms of the basis vectors. So it's given by the following, as we saw earlier. It's uj. So now we're going to use a different index. We're going to use a different dummy index, and our dummy index in this case is going to be j. Sorry, let me just wrap this out. Okay, Okay, let me write this out. So now we're using a different dummy index, okay? And the dummy, okay, let me put the I first before I do that. Okay, so now we're gonna use J as our dummy index because we already have I. So now we got Uj multiplied by Ej. That's our basis vector. So this is another way of expressing the position vector R, and we discussed that earlier. So therefore, if you're partially differentiating this product here, it's going to give you the following. Let me just write this here. We're going to get, again, we apply the product rule, okay, of derivatives. So this is the partial derivative of J with respect to Ui, okay, right? We're doing that. And we multiply this obviously by Ej, okay? We're going to add this now to Uj multiplied by the derivative of Ej with respect to Ui, okay? So we just apply the Leibniz rule or the product rule, and you can of course write it like this. You can, this is basically the chronicle delta Ji, all right, multiplied by Ej plus Uj multiplied by this partial derivative. So we can write this in terms, we can use this notation here, which is the same thing as partial derivative, you know, same thing, but we're just choosing to use this notation. Let me just write this out. You can use this notation here, partial I, EI. Okay, we'll just use this notation, which is, so the partial I basically means partial, let me write it here. Let me just make that note here. The partial I is basically equivalent to partial with respect to Ui. So we're just using a shorthand notation. Okay, so now we have this. So this is, of course, the base vector EI. Okay, this is the base vector EI. Now, what we do is we ignore this term here. So the term with the chronicle delta we ignore. All right, so we ignore this term here because it is insignificant in our derivation. Okay, so we just ignore this term here. And that, of course, implies the following. It implies, so ignoring that term implies that our base vector, EI, is equal to the following. It's equal to UI. Okay. Okay, wait, it's not UI, it's UJ. Let me fix that. It's equal to UJ. So the EI is equal to UJ multiplied by partial I EJ. Okay, that's what it means. So now we have this. So EI is equal to UJ multiplied by partial I of EJ. Okay, that's basically what we have now. So now, remember our objective is to find the derivative of EI with respect to S. So we want to find E dot EI. Okay, so therefore, this implies now that E dot EI, which is of course the derivative, okay, the derivative, which is the derivative of EI with respect to S. So this E dot EI is the derivative of EI with respect to S. So it's given by the following. So now we just go ahead and we differentiate with respect to S. We differentiate Uj partial I multiplied by Ej. So we differentiate this with respect to S. Because we need to find this E dot I. Remember, what we want to do is we want to derive this geodesic equation. And we have EI, which is a base vector here. And of course, we also have E dot I. So we want to calculate this E dot I, substitute it back in here, and then see what we get. Okay. And you know, eventually, of course, we'll get to the final version of the geodesic equation. So let's go back to our calculation here. So now we're here. Okay, so now we differentiate this, differentiate it with respect to S. Obviously, we're going to apply the product rule again. So that's going to give us the following. So we go ahead and we differentiate this Uj with respect to S. Start there. We multiply this by partial I EJ. Okay, and then we're going to say plus UJ multiplied by the derivative with respect to x of this partial I EJ. Okay, all right. So we basically apply the product rule to UJ multiplied by partial I EJ, and we get this result here. And then this is equal to the following. So this duj ds is just, we can write it as u dot j, okay, u dot j multiplied by partial I e j, and of course this term here we can ignore. This term here with the second order derivative, we can ignore this term here. Okay, so because it is of course insignificant in our derivation here, so we ignore that term, and then we have this now. That's what we have. So therefore, now we've got E dot I is equal to U dot J multiplied by partial I EJ. That's what we have now. So let me go and rewrite this on the next page. Okay, so therefore, now we've got that E dot I is equal to U dot J. It's equal to U dot J multiplied by partial I of EJ. Okay, so now that's what we have now. Now we're here. So now the next thing is the following. We take this expression here. Now we want to take this, and we want to, this expression obviously, of course, is a vector. Okay, so this thing here is a vector too. This partial derivative of this basis vector is also a vector. So therefore we can also express it in terms of the basis of the manifold. Okay, in terms of the EIs too. And we say, so we take this partial I EJ, and we express it in terms of the basis as well. And then we introduce these quantities called the Christoffel symbols. And we introduce these quantities, in this case, as simply components of this vector here along this basis. Okay, so we write it like this. So we've got K here, we've got IJ over here, and we multiply this by E K. So that's our basis vector there. Okay, so that's how we express it. We express it like this in index notation. Okay, so these quantities here basically are the components of this vector here along this basis here. All right, so now that's what we have. So we basically go in and substitute then. We substitute this in here. Okay, so when we do that, when we do the substitution, we get the following. We get that E dot I is equal to U dot J multiplied by this Christoffel symbol with a K and IJ multiplied, of course, by EK. All right, so we make the substitution. We substitute in place of partial I EJ, we substitute this expression here. So now we are now ready to go to our equation and make the substitution. So in our equation here, we are going to substitute into this, into E dot I, we're going to substitute what we got, the result that we just got. Okay, so we do that. And then when we do that, let me just write this out and go back to where I was. And so let's go ahead and do the substitution. So when we do the substitution, we get the following happening. Okay, we do the substitution, we get the following happening. We get lambda dot I multiplied by EI, okay, plus lambda I, and then we go ahead and we do the substitution. So we have lambda dot I times EI plus lambda I, and then we go ahead and we substitute. We do the substitution. All right, so what is the substitution? Well, it's as follows. It's as follows. It's U dot J multiplied by the Christoffel symbol, K, ij multiplied by ek. So we make the substitution in place of e dot I. And obviously, this is equal to the 0 vector. Okay, that's the 0 vector. So we made the substitution into our equation. So here we go. Now we're here. We would like to now, because we can see that the e's are a common factor. So what we would like to do, we would like to take out the t's. I mean, sorry, not the t's, the ei's. The e's are a common factor. So we want to take out the e's. We want to factor out the e's. But before we can do that, before we can factor out the e's, we have to interchange, or we have to change the indices, the dummy indices. We have to change the dummy indices. What I mean by that is that the dummy indices have to match. So we have an EI here. We must also have an EI here. So we have to change the dummy indices accordingly in order for us to factor out the EI, so we can get to the equation that we want. So now, this is simple, because what we do is that we change, instead of k here, we're going to put I here. And then we're going to put k here instead of I. So we just interchange them, because they are dummy indices. We can do that to them. So this is what we're going to get, okay? So we got lambda.I, that stays the same. Lambda.I, EI, we don't do anything there. And but over here, in place of I, we're going to put k. So we're going to have lambda k, and we're going to have, of course, the u dot j. The j stays the same. We don't interchange that. We don't change that. It stays there. And let me just write these first. So what I'm saying is that the j, okay, the j stays the same. So the j is there. But in place of I, we put k. We interchange the i's and the k's. So instead of having lambda I, we're going to have lambda k. And over here, instead of having I, we're going to have k. Okay. And then over here, instead of having k, we're going to have I. We'll put I here. Instead of having k here, we're going to put I here. So we just basically interchange them. Okay, they swap basically. The k's swap with the i's. And we can do this because these are dummy indices. So this is allowed. And so now we see that the EIs now have the same index. The E's have the same index, and but EI in the first term and EI in the second term. Now we can factor out the EI. So that gives us the following. We've got lambda dot I plus lambda k u dot j, Christoffel symbol I kj, okay, and we put outside, we put the EI because we factored it out because it's common to both terms. It's a common factor. All right, so you got the EI here. This is equal to 0. So we got lambda dot I plus lambda k u dot j, Christoffel symbol I kj, and then outside we got EI. Okay. So obviously we know very well that the e's are not zero vectors. So the base vectors are not 0 vectors. So therefore, that means that what's in the bracket is what's actually equal to 0. Okay, and what's in the bracket is a scalar. It's a scalar. It's equal to 0. So therefore, we've got lambda dot I plus the following. So now I'm gonna write this in a certain way. I'm gonna put the Christoffel symbol first. This is like the standard way of writing it. I'm gonna put same thing. I'm just gonna put it. I'm just gonna reorder it. I'm gonna reorder it. I'm gonna put the Christoffel symbol first, and then I'm gonna put the lambda k, and then I'm gonna put the u dot j. But this whole thing is equal to 0 because when you multiply it with e, you get the 0 vector. But we know that e, none of these e's are a 0 vector. The basis vectors, we know very well, they are not 0 vectors. So therefore, which means that this thing in the bracket is equal to 0. Okay, so now that's what we have. So to finalize this, we're gonna just remind ourselves, or we're gonna just remember that lambda k. What is lambda k? Lambda k can of course be expressed as the derivative of the position vector, and we've stated this before, that the tangent vector lambda is equal to r dot. It's the derivative of the position vector with respect to the arc length. Okay, so we stated this before. Let me just go back to the first page where we stated this. That we stated that lambda is equal to r dot s. Okay, so you can express lambda, the tangent vector, you can express it, of course, as r dot s. That's the derivative of the position vector with respect to the arc length. Okay, so now we're going back to that statement. So let me write it down again. So lambda k basically is equal to r dot s. All right. Which of course is equal to u dot k. All right. So lambda k is equal to r dot s. It's the derivative of the position vector. And the components of the position vector, of course, are the coordinates, ui's, in this case, the uk's. Okay, you can express, of course, you can express the position vector as uk, ek. So if you differentiate the position vector with respect to s, you are going to get u dot k. Okay, you're going to differentiate the components. So r dot s is equal to u dot k, basically. All right, and which of course is the same thing as the derivative of uk with respect to s. All right, and obviously this implies that when you differentiate this now, if you go and differentiate this, okay, if you have lambda I and you differentiate lambda I with respect to s, you get the following. Okay, now you have to differentiate with respect to x the derivative of ui, okay, with respect to s, because we see that lambda I is the derivative of ui with respect to s. So the derivative of lambda I, which is lambda dot I, is equal to the derivative of this derivative ui with respect to s. So that basically gives you a second order derivative of ui with respect to the arc length. It gives you this. Okay, so now we can go ahead and substitute these into our equation here. So in place of lambda dot I, we're going to put this d squared ui with respect to s squared. Okay, and then we have, of course, plus Christoffel symbol. Let me make sure everything is. We have plus Christoffel symbol I kj. Okay, kj duk ds. So now we're substituting what we have here above here, and of course multiplied by duj ds. Okay, so that d squared ui ds squared plus Christoffel symbol I kj multiplied by duk ds times duj ds is equal to 0. Okay, so guys, that's what we have here. All right, and this is the final equation. This is the geodesic equation, the general geodesic equation. Okay. All right, let me just. All right, so this is our final result.